So we're picking back up in the middle of section 3.3. We are looking at subtraction of whole numbers, and we are at the point where we've talked about some of the models, and we're going to take a look at properties. So we did properties of whole number addition, and these are the same properties listed again. And what we're going to do in this series of questions is examine whether or not these properties, which hold for addition, also hold for subtraction. Okay? So the first one was the closure property. The closure property is often the one that trips people up in their head the most about what it means. So closure just means you're able to take whatever the number group is that you're working with, this is whole numbers, and you're able to employ whatever the operation, we're working with subtraction, and when you take any two numbers with that operation, you still get a number that's a whole number. So it worked for addition, for example, if we did 3 plus 2, right? Those are two whole numbers. And when we add them together, we get another whole number. And it happens every single time. That's why we say the whole numbers are closed with respect to addition. The question is, does that work for subtraction? If I take any two whole numbers and I subtract them, will I always get a whole number? No. Can you think of an example? Awesome. So this one does not hold. And we're doing what are called counterexamples. Do you remember that phrase from back in chapter 1? A counterexamples means an example that shows something doesn't work. And counterexamples are really nice because when you show something doesn't work, you only have to give one example of it not working. And so that's great. And the one that Zion gave is great. So 4 minus 7. 4 minus 7, which is negative 3. I mean, it's a value, but this is not an element of the whole numbers. Remember that notation? It's not one of them. It's negative. And once I write that one up there, you can probably think of a lot more examples that would fit in that category now, right? So if I asked you again, is it closed with respect to addition? The answer is yes. But is it closed with respect to subtraction? The answer is no, because we've got lots of examples where it fails. Commutative property. So remember what commutative was? Commutative means you can take the order and you can flip it. And we push into this really heavily in the elementary grades when we teach, think flashcard addition with children, right? If we learn all of our plus ones, right? 7 plus 1 and 8 plus 1 and 9 plus 1 and all those. Well, when we get to the fact that we're adding nines, we get some of those for free. I don't need to reteach what is 9 plus 1, because I already taught you what 1 plus 9 was, right? That's commutative. The order of addition doesn't matter. The question is that true for subtraction? Does the order matter? Okay, so Tessa says, yes, the order matters. So if the order matters, Tessa, this means that this would not be true, right? So this does not hold. Can you give me an example? Just give me two numbers. They gotta be whole numbers. 5 and 12, fantastic. So if I take, actually, let me put it the other way just so I've got it in order 1. If I did 5 minus 12, we'd be good to go. That's a whole number. But if I switch the order and I do 5 minus 12, it's not the same value. Now it's interesting, right? Because it is the same value, it's just the wrong sign. Right? It's the same number. Both of these end up giving me the same 7, right, when I do subtraction of it. But one's positive and one's negative. So they're not the same. And because they're not the same, commutative property fails. Okay, so no commutative property. Associative property. So associative property, if you remember, is the grouping. It's how we group numbers together. And it's designated usually by parentheses, like grouping symbols. And almost any example you can come up with is going to fail on this. Let's just put that there, okay? So I'm going to give you an example just because it's going to keep our values positive longer, then they will turn negative very quickly. Let's see if I have mine written down. Yep, so let's do 3 minus 2, and then minus 1. So this would be an example with some parentheses, right? So 3 minus 2 is 1, thank you, and 2, and then you have that 1 minus the 1 and you'd get 0. That's a whole number. Like this value still gives me a whole number. But the question is, does it equal when I do the order differently? In other words, if the parentheses are around the 2 minus 1 instead of around the 3 minus 2, so let's check. Well, what is 2 minus 1? 1. And what is 3 minus 1? 2. I still got a whole number, but I did not get the same whole number that I got on the other side, right? So associative property doesn't hold either. And just about any numbers you pick are going to fail with this. It's not going to be like, I have to just pick the right ones. But I wanted you to see one that kept everything actually in the whole number system. So even just keeping everything whole doesn't actually still achieve the goal of it working with this example. It's not enough. Identity property. People get tripped up on this one. This is probably the most common one for people to get tripped up on. So the identity property with addition means that there's a number that I can add to something and it doesn't change it. What number is that? What number can I add to something and it won't change it? What does it implicate? 0, right? If I add 0 to something, it won't change the value, right? That looks great. But the kicker is that number, so that number 0 is called the identity element. It's the element that I add. But I have to be able to add it in either order. So if I add 0 plus 7 or 7 plus 0, both of them give me back 7. That's what makes it the identity. Does that work for subtraction? Anna says no. Can you give me an example, Anna?
Like 0 minus 7?
Sure. We'll do the 7 again, okay? This is a no. If I did 7 minus 0, I almost feel like it works, right? 7 minus 0 is 7. That's exactly what we would expect from an identity element. But the fact is we have to do it in the other order, and when I do it in the other order, it does not equal 7. So it's not an identity element because it has to work in both orders. And you almost get this one for free, that it's not going to have an identity because the commutative property already failed, right? Now, could the commutative property fail and there still be a 0? Perhaps. But it does seem reasonable that if one of them failed and now I'm switching something around, that the other one's going to fail too. All right, so what we just discovered is there are no properties that hold for subtraction. That's what we discovered, right? All the 4 properties that held for addition all fail for subtraction. So we don't get these properties for free. It's not just like, well, obviously it works that way. Well, it did for addition, and it failed everywhere for subtraction. The fact that we're working with addition or subtraction matters. It changes the properties. So the majority of what we're going to do next, the biggest bulk of this section, is algorithms. Algorithm is a fancy way of saying how to do something. The process, the way in which we do something, okay? So this is the way in which we subtract. How do we subtract? And you may be surprised to know, and maybe not surprised to know, that there's actually more than one way to do subtraction. I will say that there's one way that even when we teach the kids really young how to do them on all these ways, there's one that we tend to sort of gravitate towards anyway, and it's the one that you're familiar with, okay? But establishing how subtraction works and why, it's really nice to have more than one way to show it. It's really nice. So our concrete model is our first one, and a concrete model is much like the concrete model with addition. So if you'll remember, we talked about like Legos being stuck together and broken apart and things like that when we were doing with addition. We're going to do the same thing here. So this one is 34 minus 18. So we're going to do 34, and 34 means I'm going to have 3 longs. And they should all be the same size, and they're not, but you can pretend, okay? 3 longs. And I have 4 units, so 4 little boxes. And what I want to do is I want to take away 1 long. That's fine, I can take away 1 long. There's 3 of them there, I just take one of them away. And I want to take away 8 units. And that's the problem with this one, right? I don't have 8 units to take away. There's only 4 of them here. So what would we physically do? Like we're doing this virtually on the board. If you were doing this in a classroom physically, you'd have little Lego blocks, right? You'd have these number cubes that you could actually break apart. Tactile learning, physical stuff, right? Kinesthetic kind of things. So if you're taking a look at this, what would we physically do in order to have enough units to take this away? Do you remember what those longs are made up of? They're made up of 10 what? They're made up of 10 units. So while we don't usually draw them in on my board, can you imagine if I did? I'll draw one of them in, and they're not going to be very good. So that's your warning. Okay, I told you. Those are all supposed to be the same size. They're not, and I think there's 10 of them. I think I counted the parts right. So there's 10 little units, and we physically took them like Legos and broke them all apart. So what happens is that I end up with only 2 longs now, right? I haven't taken anything away. I'm just rewriting the way that this looks now. Instead of 4 units, wow, that's not good at all. I have how many? How many? 14. Thank you. 2, 3, 4, 6. Oh, goodness. Tools are good until you don't get them quite accurate enough. I think that's 14. I think I've got 14 of them there. Okay, is that all right? I had 4. I took a long. It was 10. I broke it into little bitty pieces, so now I have 14 little units. And so now I can actually look at this and I can actually remove, right, physically from the pile of blocks, I can remove the things that I want to remove. So the first thing I want to know that I want to remove, it doesn't really matter which order, but I'm going to remove one of these. One of them is gone. Okay, one of the longs is gone because it told me I'm supposed to remove 1 long and 8 units. And then I'm supposed to remove 8 units. So I need to catch 8 of these guys and I need to remove them. So 8 of those are also being removed. And then the question is, what remains? Well, I know I have 1 long that remains. What else remains? How many? 6. There are 6 units. Okay. Trying to make my units look like squares and not circles. Okay, so this is the answer. Right, in my pile of blocks sitting in my hand on my desk on the floor next to me, right? And I can count and I can tell you how much remains. What is it that remains? What number is this? 16. Yep. So this is a concrete model. This is the little ones, right? Maybe not even this big in numbers, but this is your pre-K kindergarten kids. They're using concrete models all the time. And you might be sort of even led to think, well, they're not really subtracting, they're just counting. And they kind of are, but they're doing a counting model for subtraction. That's what this is, concrete model. All right, the next one is the one that you know. This is the standard algorithm. This is the one where you're going to gravitate towards as you progress beyond those early elementary grades, even if it's not the one you start with. And it looks like this. And the first thing that's a little awkward about this particular algorithm that you are comfortable and familiar with is that unlike everything else that you do not move from left to right. Think about that for a second. How do the kids read? How do they write? Everything's left to right. And all of a sudden now you're supposed to be doing something right to left, just like with addition with this particular algorithm, right? Moving from right to left is a little bit odd. Truthfully, it's a little odd. But that is what we do when we do the standard algorithm. And we go over here and we count, or we subtract in this case. And we say, okay, well, I can't subtract 4 minus 8. That's not possible. There's not enough to take away. And so I have to regroup. Regroup language sort of puts us back in that concrete model. I need to take something and I need to break it apart. So I'm going to take a number, it's a long, right, one of these numbers here, and I'm going to borrow, or I'm going to regroup it so that there's only 2 of them here. And when I break it all apart, because it was 10 long, it's going to have 10 of those individual pieces that are now combined with the 4 individuals that I already have here. And this is what I physically have. I have 14 now minus 8 for the 6, and I have the 2 minus 1 for the 1. So I have 16. That's what we're doing when we're borrowing. Why did 1 become 10? Well, it didn't really, right? It was 10 all the way along. It was in the 10s column is why. So when we took it away, we took away 10, which is a 1 in the 10s column. That's what's happening here, and you can justify it visually from this particular, algorithm. You can see that's what happened. Right? I took a long and I broke it apart into 10 little units. Now there's one that's sort of in between that approach. This is called the expanded algorithm. So the expanded algorithm looks like this. So we're, instead of writing it as 34, we're going to write it as 30 and 4 separately. And we're going to write it as subtracting 18 and subtracting 10, and subtracting 8. So we're breaking it apart by place value. So we're recognizing that 34 is 30 and 4, and 18 is 10 and 8. And the reason there's 2 subtractions here is because I'm supposed to be subtracting all of that from the first number. Does that make sense? Okay, so if I break it apart like this is sort of in between concrete and standard. I can see that when I take something away here and I make the 30 become a 20, I'm really taking away 10. And I'm regrouping that 10 over here with the 4 so that it's now 14. I'm just shifting 10 of those little guys from one place to the next. More helpful. And then I can subtract. This is what happens when you change money out in drawers. Has anybody ever worked concession stands or a garage sale or something where somebody comes up and says, I need change for a 1. They want quarters. Aldi. This happens at Aldi when you get the quarters to use the carts, right? Well, you're not giving them anything. They're not giving you anything. You're just doing an exchange. That's what's happening here. We're exchanging. And then we're able to subtract because they're lined up more conveniently. 14 minus 8 would be our 6. And then 20 minus 10 would be our 10. And our answer would be 16. It's an expanded algorithm where we can really see how this is working. But not with objects, right? Still more abstract because it's numbers. Okay, the next one looks quite different. You ready for this one? Okay, the next one's called equal additions algorithm. So notice I've got some bigger numbers. The reason I'm using bigger numbers is because this is a more convenient method when the numbers are bigger. It feels a little bit silly when the numbers are small. Okay, so I don't want you to look at this and say, well, that was stupid. Why do we do that? Well, if I give you bigger numbers, you can at least see there's some value in it and why. So we're going to write this like we did before on the others, where I have 834 minus 158. I'm going to write it like that. Okay. Now, instead of regrouping, the goal here is to subtract zeros. I'm hoping if I write that down, you will too. The goal is to subtract zeros. So right now, everything in that bottom row is not a 0. Y'all with me on that? My goal is to have zeros everywhere except for the first number. I'm not going to have a 0 in the first place, but I need zeros everywhere else. So the way that happens is that we take a look at the number 8 at the end and we ask ourselves, well, how much would I have to add to this 8 to make it a 0? I don't want to take 8 away. What could I add to this to make it 0? Don't overthink this. 2. If I added a 2 here, I know I've got to make up for that, right? There's a balance here going on. But if I added a 2 here, what's 158 plus 2? 160, and now I have at least one of the zeros I was looking for. But the balance, right, the compensation is that if I'm trying to subtract these two quantities and I decrease this one a little bit, because that's what I've done and I've moved it down, I have a balance, which means I have to decrease this one a little bit too. You decrease one, you got to decrease the other, right? So it's kind of like the idea is that if I was standing on a stair and my son, who's back today from his program, it's very exciting, he was standing on a stair, right? If we're standing on stairs next to each other and we both took one step down, right? Our height difference would be exactly like it was before because we both decreased the same amount. That's what's happening here. So this one, we're adding, so we're stepping up, right? So we're stepping up that same amount. So we're adding a 2, but if we add 2 to the bottom, I got to add 2 to the top. That's my balancing point. So that's 836. Now I've got almost what I need. I've got the 0 in the ones place, but I need a 0 in the tens place as well. What would I have to add to 6? Just think about the number 6 itself to make a 6 become a 0. 4. But since the 6 is in the tens place, what will I add? 40. I will add 40. Okay, does that make sense? 6 I add 4, so 60 I add 40. I'm going to add 40 to both these numbers. So the number on bottom, what's 160 plus 40? 200. And the number on top, 836, add 40, what do I get? 876. Why? Well, because subtracting zeros is easy, right? This problem at the end is the exact same answer as the problem at the beginning, but it's much easier to do. It's much easier to do. So what is 876 minus 200? 676. You got it. This one took 2 steps to get there, right? It took 2 steps to get there. If you had zeroed it out and there's only 1 step, then there's only 1 step. So it doesn't always take 2 steps to get there. All right, so let's see what happens in other bases, because like we talked about before, our sort of foyer, our exposure to other bases is to make us feel a little bit uncomfortable because we're real comfortable with subtraction. You've been doing it for a lot of years. And the little ones that some of you guys are going to teach are just now learning it, right? Especially if they're learning it with numbers that aren't just single digits. 8 minus 5, okay, fine. But what if I have 852 minus, 176? I don't know. right? Like that's way different because it's a longer number. So we're going to take a look at what happens in other bases to give ourselves some feel for how these things work. So recall, we're going to look here at base 8 specifically. There's nothing special about base 8. It's just the one that I picked, okay? So you're going to see 5s and 2s and different things all over your book. This one's 8. So it says we've got 3, 4 base 8 minus 1, 7 base 8. So we're going to write this just like we did on our others, but we need to keep in mind we do not have an 8 or a 9 in base 8, right? No 8s, no 9s. It's 0 through 7. So I'm going to show you the standard algorithm for this one first, okay, just what that looks like in standard, okay? And then let's do equal addition, not equal additions, let's do the expanded one on this one. We're just going to do a couple of algorithms so you can see the difference. All right, so I still, just like in my own algorithm that I, have worked with my number systems that I'm familiar with, I still can't take 7 away from 4, correct? So I have to regroup. So I take my 3 and I decrease it by 1. And my 4 increases, but it doesn't increase by 10. How much will it increase by? 8. Why 8? Because we're in base 8. Okay, so it's still a long. There's still a physical object that's 8 units long, right? But when I break it apart, there's only 8 of them now that are getting grouped with the other 4 that I already have. So I don't have 4, and I no longer have 4. It doesn't become 14, though. It actually becomes 12 because I only am borrowing or regrouping 8. So this is now a 12. So what is 12 minus 7? 5. And what is 2 minus 1? 1. And this is base 8. Okay, so let's see it in the expanded algorithm so that we have another sort of picture. And expanded, we see this is 30 plus 4 minus 10 minus 7. That's what it would look like. So, I would have no problem doing the 30 minus 10. That'd be great. But I still can't do 4 minus 7. Right? So I break this 30, this 3, 0, down into 2, 0, because I'm borrowing, a whole grouping of them. But a grouping, or the number 1, 0 in this base, is as big as 8. So when I borrow it, it still becomes a 12 here. I'm borrowing 8 in base 8. If I were in 7, I'd be borrowing 7. If I were in 12, I would be borrowing 12. Okay? So it's all based on the base that we're in. And then I can do my subtraction just like I did on the other one. And I get 5 here, and I get 1, 0 here. And this is 1, 5, base 8. And just like we talked about back in section 2, when we're doing bases like this, we have to write the subscript. Okay, all good? Okay, let's try another one. We're going to do base 3. It has digits 0, 1, 2, and that's it. No 3s or higher in base 3. So again, I'm going to show it to you with the standard algorithm, the one that you think you're very comfortable with and really work well with, because our goal is to get a little uncomfortable with it, at least with the method. Okay, so first of all, notice there's no need to do anything in the ones column, right? It is happy day. I can just do 2 minus 0 and I'm good to go. It's 2. So don't complicate things. If the subtraction is simply available to be done, just do it. But when I get over to the 3s column, which is the one that's next to the 1s column now, right? The second column over, I have a problem because it says 0 on top and has 1 on bottom, and I can't do that. Correct? So I need to regroup. But when I go over to the 3 squareds column, there's nothing there to regroup from either. So I have to go over one more time into the 3 cubes column where there's a 1. Can you picture that happening? I'm looking over here and I'm saying, hey, can I borrow some money? They say, I don't have any. They say, borrow it, borrow it. Got to go all the way over there to borrow something, right? I got to get all the way over there to regroup. So I'm going to take what's in that column and I'm going to regroup from it. This 1 will become a 0. But what base am I in? 3. So what am I going to be regrouping? 3. When I borrow or regroup in base 3, it's with the number 3. So it's going to be a 3 here. Now there is something there that I can regroup to the next column back. So I'm working my way backwards. So I can take away, let me move this down a little bit. So I can take away one of these from the 3 to make it a 2, right? I'm going to regroup that. And this 0 now becomes a 3 because we're in base 3, right? So I have 3 minus 1 now, 2. 2 minus 1, 1. And this is 1, 2, 2, base 3. Let me do the other one as equal additions, because that's the one that's the most different. 1, 0, 0, 2 minus 1, 1, 0. Now the goal in the base or in the equal additions is that I end up with zeros down here, and I've got one of them already, so I'm already partway there on this one. That's kind of nice. I only have to worry about this one right here, because right now it's the only other digit to deal with. How do I get that 1 to become a 0? We need to add 9 in our system, but this is base 3, so what would I need to add? I need to add a 2. Okay, so in this system, 1 plus 2 is equal to 1, 0, because there is no 3, right? I run out of digits. So it's a 2 that I would need to add in that second column over, so it's 2, 0. But if I add it to the second number, I have to add it to the first number. It's a balance, it's the stair steps. So on top, I have 1, 0, 2, 2. And on bottom, well, I have a 0, and I have a 0. And then what happens when I add this 2 to this 1? What's it become? It's 2 to this 1, sorry. It becomes a 1, 0, right? It would become a 3, but I don't have any 3s. It becomes a 1, 0. So that 0 is happening here. And that 1 carries over here. And now I have a 2 here. It's a little uncomfortable, right? It's okay. When I add and I get what would be a value of the base 3, there's no 3s, so I have to have a 1, 0. The 1 moves over into the next column, increasing that to a 2. Now there is 0, 0, but now I have a 2, and technically the 0 under the 2 still would create a need for borrowing, right? That's not what we want. Our goal is not to have any borrowing. So we need to do this one more time. What would I need to add to the 2, this 2 right here, to make it a 0? Y'all know. What do I have to add to 2 to get 0? 1. I would need to add a 1, right? Like 2, 0, 0 has to add 1, 0, 0. That's what I'm doing. If I add a 1 there, I have to add a 1 up here. Whoops. On the top, it's now 1, 1, 2, 2. Though that one usually adds together really nicely. I've still got zeros in the 1's place and the 3's place. But when I add this 1 to this 2, what is 1 plus 2 in base 3? What is it? It would have been 3 in our base, but there's no 3. So what's 1 plus 2 in base 3? 1, 0. So I have a 0 in the 3 squareds place, and I have a 1 over here now in the 3 cubes place. Make sure I was saying it right. And again, the lovely thing that happens is that end up the subtraction that's really clean and easy. So I have 2, I have 2, I have 1, and then in the third column over, fourth column over rather, I have 1, 1, 0, and this is base 3. Same answer, different perspective. Now, for the most part, I don't think they tell you which algorithm to do these in. So you can pick. So if you actually looked like that and you were like, that was terrible, why would I ever want to use that algorithm? Okay, maybe you wouldn't. But maybe you would be okay with it if we had done it in base 10, but you're not liking it in base 3. That'd be okay too, right? You don't have to like them all equally. But you do have to show me something. You cannot go from 1, 0, 0, 2 minus 1, 1, 0 to give me 1, 2, 2 base 3 and have not done any work. You got to show something. So whatever method you're using will involve showing work, right? I know you got the back of the book to check your answers. That's not the point. Okay, it will involve showing some work, so make sure to do that. All right, the last part of this section involves mental math, and I think there's one more thing in here, isn't it? Oh, no, it's all mental math that's left. Okay, mental math. Mental math means it's stuff that you can do in your head, but you have to write it down on paper because I can't see inside your head. That's what it is. So it needs to be something we can do, small amount of steps, hold it in our head for those into pieces. Like it has to be something I can reasonably think through without writing it down. But I'm going to write it down for the sake of my professor because she hasn't learned how to read my brain yet. That's what you're going to do. Cool? You don't want me to read your brain, do you, Allie? Not really. Probably not a good idea. Yeah, so this is what we're going to do as a substitute. So we have 4, 6 minus 3, 8. So breaking up and bridging is our first one. So the way that this method works is that we take our second number and we break it apart. Okay, 30 and 8. Cool. And we take the original number we started with, is 46, and we subtract off 30. Subtract the larger of the values. Okay, so 46 minus 30 is 16, thank you. And then we subtract off the 8 after that because we've got a smaller number to work with. So 16 minus 8, that would be a subtraction fact that we might have memorized by that point, and we would get 8. This is called breaking up and bridging. So we break it up into the 30 and the 8, and then we bridge by doing both pieces. Count how many steps this took us to do. Well, it took one step right here, right? I subtracted, well, actually I should do this. I broke it apart. The 30 and the 8 were broken apart. That's sort of step 1. Subtracting and getting the 16 was step 2. Subtracting and getting an 8 was step 3. Okay, mental math, 3 steps or less. If it's more than 3 steps, the majority of your kids at this age would not be able to do that in their head. Therefore, it's no longer mental math. Okay? So you have to make sure that whatever you're telling me is mental math is a 3-step or less process. Okay, trading off. Trading off is really just equal additions. You may like it better in this one. We'll see. You may not. But we have 46 and we have 38. And our goal is that we're not going to borrow. And so we want to get a 0. What would I have to add to 38 to make it the next nice value instead? 2, right? If I added 2 to 38, that would be so much nicer. 40 is a much more convenient number. But if I add 2 to 38, I have to add 2 to 46, making it 48, and then I can subtract, giving me 8. Do you count 3 steps? I think so, right? 3 steps. This is much more convenient. I actually will do this with small numbers. I will do this in my head sometimes, actually. Like when I'm at the grocery store, I want to figure out if I've got enough money or something, do some subtraction or something. This I will do. I will move things up a little bit and see if I can still subtract and get something easier to subtract with. And the last one, and it's usable in certain circumstances and not others, but that's often the case with lots of these methods. It's called dropping the zeros. And what dropping the zeros does is it happens when there's lots of zeros. And what it really just means is we're going to ignore them for a minute. We're just going to pretend like they're not there. So we're going to ignore the zeros for the moment, and we're going to pretend like the numbers are really 46 minus 34. Or if you prefer, like this. So what's 46 minus 34? 12, thank you. We got 12, and then our last step is to put the zeros back on. Okay? There's nothing super special about it, but we're just making the numbers smaller in our head to work with, right? The numbers themselves don't change. The equal additions, the numbers change. These numbers don't change. They just become smaller to think about, okay?